Good afternoon, good evening to everyone. We are delighted to start the talk series of the Fall Displacement Hazard Laboratory with Alex Sarmiento. We thank Alex for accepting our invitation. Alex is a seismic hazard analyst and scientist with a significant experience in seismic hazard evaluations for critical infrastructure projects. For the last 5 years, Alex has been working as a project scientist at the University of California, Los Angeles, with Professor Bozornia in a project titled Fall Displacement Hazard Initiative. And Alex is the first author of the report GEARS, Fall Displacement Hazard Initiative database, published in 2021, and co-authored other publications related to the project. Today, Alex will talk about this project, the results, and future steps. The talk will be about 40 minutes long, more or less, and then we have time for questions. So please, Alex.
Yes. Oh, thank you. All right. We practiced the screen sharing. Let's see if I can still do it correctly. Let's see. How is this? Is it looking good?
Yes, it is.
Perfect.
Let me do the little laser pointer. Alrighty. Yeah, so good afternoon, everyone, and thanks so much to Paolo and the organization for inviting me to give the talk today. Like Paolo said, my name is Alex Sarmiento, and I'm working under the guidance of Professor Bozornia at UCLA for this research program that is focused on fault displacement hazard. And so today I'll talk about the program and what we've achieved so far and some of the next steps. So I'll start off with an overview of the Fault Displacement Hazard Initiative, or how do you say, FDHI project. I'll give a very brief high-level overview of fault displacement hazard analysis to help us maybe understand the FDHI project goals and the results to date. And then towards the end, it maybe is a good opportunity to talk about future research needs. And to support that conversation, I want to highlight some concurrent research that has been happening outside the FDHI project, but still, in the last 4 or 5 years. So there has been a lot of momentum in Europe and the US to update the state of practice for fault rupture hazard. In particular, Stefan Bayes and at IRSN and his colleagues back in, I think, maybe 2015, started a new effort to create a modern database for fault rupture and displacement. And it was related to the workshop that I think was in Rome. And around the same time, utility companies in California were pulling together funding to look at updating fault rupture hazard evaluations. And so things really came together at the end of 2016 at a big workshop in Northern California that brought together the research groups in Europe and the US and all over the world. And not too long after, the FDHI project kicked off. The overall goal of the FDHI project is to update the state of practice in fault displacement hazard analysis. The project is a community-based research effort with several phases of study. And we have so many phases because fault displacement hazard analysis actually has a lot of different components, and there's takes some time and planning to systematically tackle each part. The project has the community includes teams of geologists and engineers and model developers from literally all over the world, including some folks in I think in the room today. And if anyone here is familiar with the ground motion modeling projects that have come out of Berkeley and Pierre, similar to that philosophy, we really think that we can accomplish more as a group than as individuals. And so these sort of structured research programs are becoming more and more popular, at least for geosciences in the US. So with these structured research programs, we typically hold monthly project meetings for all the participants. And we've been doing this now for 5 years. And at these meetings, each research group or model team has a chance to present their progress and ask other experts for advice and opinions on technical matters. It's a really supportive and supportive group. It's not competitive or anything. And honestly, it's a lot of fun to get the same group of experts together on a regular basis to talk about really specialized and technical things. And then, of course, there are other ongoing meetings with the different smaller research groups that happen as well. And so all of these, this kind of organized research effort works towards usually these same 3 steps. We usually will start off by publishing the results or the products as technical reports. And this is the key way that we can make sure everything is available for free to the public for easily to download. And then in parallel or maybe slightly in sequence, we go through the journal publication process, and that's the phase we are in now. And then usually once the journal papers are out, or sometimes when we do the technical reports, we try to hold public workshops for the engineering community so that we can raise awareness about the new work and help people understand how to use the models. And I'll bring this up a little bit later in the talk, but the technical reports are available online for free. And I think the easiest way to find them is if you search UCLA FDHI, this should be the first page that comes up, and then you can go to the sidebar and find links to reports. Alrighty, so that's organizational stuff. Now let's talk a little bit about fault displacement hazard analysis. So no surprise, I'm sure, to the folks here in this room, it turns out that principal and distributed ruptures are very different. And so we treat them differently in the model development and the hazard analysis. And of course, the sort of convention is that principal ruptures are on the faults that are associated with the fault plane that generated the earthquake. And these they tend to be more continuous, more structurally coherent, and spatially organized. They have the larger displacements as opposed to distributed faults, which are the splays and secondary or tertiary ruptures. And these are usually shorter, discontinuous, and have the smaller displacements. There's really different causative factors for these, different driving mechanisms, and so they manifest differently, and we have to handle them differently, you know, in the model development and hazard analysis. And a lot of this kind of articulation of this goes back to work in the late 1990s for the Yucca Mountain Nuclear Repository Study Site in Nevada, and with the Coppersmith Youngs and that whole cast of experts. So for fault displacement hazard analysis, there are two types of models that we need. First, we need a model for the amount of fault displacement. And these typically almost always provide a probability density function for a displacement amplitude. The models for principal and distributed faulting are totally different. They use different data and different predictor variables, but the concept is the same in that we're still defining displacement as a continuous probability distribution. And then the second type of model that we need for fault displacement analysis is models for the probability of surface rupture. Of course, not all earthquakes rupture the surface, and even when they do, we can have gaps in the principal rupture, and the spatial distribution of distributed faults is highly variable. So we have different elements of probability rupture models that try to tackle all of these, I guess, problems or issues. And maybe an important thing to think about is that for these rupture probability models, these models for rupture occurrence they're all probabilities. So that means they're just fractions or percentages. They're not like a probability density function for displacement. And because these are just the fractions or percentages, they really are, in analysis, they are just scalar multipliers on the y-axis of our hazard curve in a probabilistic analysis. And in deterministic analysis, we actually don't consider rupture probability because this only affects the rate. It only affects our y-axis, so to speak. And we don't use rates in deterministic analysis. So with kind of that in mind, we have a lot of different elements that we need to consider for fault displacement hazard analysis. We have models for principal and distributed displacement amplitude, and then we have a whole suite of rupture probability models. And it turns out that for the current state of practice, there are not very many models. This table here is essentially a summary of the models that were available when we started the modeling part of the project in 2020. And I won't go through all of the details here, but the point is there's not very many models. They all fit on one table that we could actually read and go through here if we wanted. There's usually only one model per style of faulting. Most models are over 10 years old. So this, I think, really highlights the fact that there is a big need to update the state of practice. And so that's kind of hopefully a good segue into where we are now in the FDHI project. We've developed one new database of surface rupturing earthquakes and 4 new models for fault displacement hazard analysis. And I'll talk about each of these in a few more slides here. For the models, the most are focused on principal displacements. Some have considered distributed displacement and some of the conditional rupture probabilities, but most are focused on the displacement amplitude, that probability density function. And I do want to make a quick note that the database contains, we'll talk about only surface rupturing earthquakes. So that problem of what's the probability that an earthquake produces rupture anywhere, that general probability of surface rupture. At this point, we're not developing empirical models for that because we don't have the full empirical database for it. But let's go ahead and talk a little bit about what is in the database of these surface rupturing earthquakes. So there's 75 shallow crustal surface rupturing earthquakes for all styles of faulting. This plot up here is the magnitude distribution. We're a little bit narrow in the normal faulting for the magnitude range, but not too bad for strike slip and reverse earthquakes. We have some smaller and some larger, which is nice. There's geospatial control for all of the ruptures and measurements, so geographic coordinates. And there are over 40,000 fault displacement measurements for all of the components, like a lateral, vertical, all of that adds up to over 40,000 measurements. And we have geologic data for a little over 26,000 measurement sites. And then all of the ruptures and measurements are classified as principal or distributed faulting. And I will say that in the case of very wide aperture measurements, like you might get from optical image correlation or something similar, those actually have their own classification. They're not really principal or distributed, but total. So the database was developed for the model developers. And so this makes it a little bit different from some of the other databases in terms of the content and the organization. For example, we have an event coordinate system for each earthquake that projects the data into a launch strike sense, and those coordinates are in the database. So this is nice because it allows anyone to very easily create slip profiles to support analysis or just visualization. And also, if you want to look at the strike normal distance, which is useful for distributed faulting, that information is in there as well in that coordinate system. We also developed quality codes for all of the measurements, and we explicitly identify sites that have multiple measurements that are, how do you say, technically defensible alternative interpretations of a slip measurement. And most of the models are developed for net displacement. Most of the new models in FDHI are developed for net displacement instead of a specific component. And so we had to develop the best estimate for net displacement amplitudes from the reported slip components. And we've done that, and we provide recommendations on the completeness and reliability of those net values based on our quality codes and the alternative measurements. And so to do all of this, we actually put a lot of effort into the quality assurance and quality control and reviewed everything very systematically and in quite a bit of detail. So as I think Paolo mentioned at the beginning, we've published the technical report for the database a couple years ago, and it describes that process of creating the database and discusses that extra information that is interpreted for the model developers. And the report also includes flat files that have measurement and rupture data in 3 different formats, CSV, KMZ, and shapefiles. You can download everything easily for free. And again, if you just search UCLA FDHI and databases on the side, it will be a link to the reports. And importantly, we are finishing up the manuscript very soon for the database, and so it should be submitted to Earthquake Spectra and very soon, hopefully. Okay, so let's maybe talk more about the new models. If folks here are familiar with any of the existing models, there's actually a lot of different approaches that are used, and there can be a lot of nuance in what's available in the models and how they should be applied. And that is this kind of the nature of fault displacement hazard analysis at this point in time. I could easily spend 30 minutes on each of these 4 new models going over all of the little details, but you know, we can't do that today, so I will just try to give a high-level overview. To kind of help us understand what the new models have to offer in terms of all of those different components of fault displacement hazard analysis, we should talk a little bit about the model formulations. So we'll start with the principal fault displacement. I think it's most common and easiest to kind of wrap our heads around. All of these models are kind of set up the same way in that we are predicting the displacement amplitude as a continuous probability distribution based on the size of the earthquake and our position or along the length of the surface rupture. And so we know from displacement profiles from many earthquakes that the slip varies as we move along the length of the rupture. Particular really big tapers at the end of the rupture are common. This is actual data from the 1987 Superstition Hills earthquake. And we can see some variability along the rupture. Incidentally, these dips are where we have different segments. So to account for this variability as we move along the strike, the models use what is called a normalized position along the rupture. So the surface rupture length is normalized to take out the effect of earthquake size there, and we'll put it back in the another part of the model. And so when we look at the variability of displacement along the strike of the fault, we see in this example here from the Peterson model, the displacement amplitude increases as we move along this normalized position. And importantly, we treat the displacement as that probability density function. So one of the nuances of this is that the ruptures are not symmetrical. There's usually the peak or maximum displacement. Of course, it does not always occur in the center. And so we have asymmetry in our slip profiles. And most models, to avoid having to deal with that in a forward prediction, will actually take slip profiles and fold them across the midpoints. And so it's very common to see these plots like this that end at 0.5 instead of 1. And this is just a folded slip profile. And then one last little note here is that instead of there are some models that follow all of this, and then instead of predicting displacement itself, they predict a normalized displacement. So the D over the average displacement or D over MD. And in those cases, the earthquake size is not part of the, it's not a predictor variable in the model, but instead it's kind of handled by this normalization factor. And the upshot of all this is that it's the responsibility of the hazard analyst to make sure the aleatory variability in earthquake size does get incorporated in the calculations. So that's we can maybe summarize those concepts from the previous slide by putting them into two categories. One is just thinking about how these models for principal fault displacements are set up. You can describe it as the model formulation is essentially a shorthand notation that tells us what the model is predicting or the response variable, and how the aleatory variability is modeled, or the statistical distribution. And so maybe a common shorthand notation you've seen probably is, for example, the Peterson, one of the Peterson 2011 models predicts a natural log of displacement using a normal distribution. In the Young's 2003, for example, one of their normalized models uses D over MD with the beta distribution. So this sort of format for the model formulation tells us what is being predicted and how the aleatory variability is being modeled. And then the second part is it's convenient to think about the components of the model in terms of location scaling, which is just that shape of the median slip profile, and then a magnitude or earthquake size scaling, and that's what slides the displacement amplitude up and down. These aren't necessarily developed separately. Sometimes they are, but essentially, I think this is kind of a conceptual roadmap for what the model is trying to do and how the parameters or variables fit in. So the examples that we gave on the last two slides, we're talking about principal displacement. And now is kind of a good time to mention that most of the new models in the FDHI project predict what's called an aggregated displacement instead of principal displacement. And when we say aggregated, we really just mean the sum of displacements across parallel or subparallel ruptures. So this is a kind of a schematic map here. And if we have a rupture that goes left to right across the screen, we have the different locations along the rupture, data from parallel principal ruptures and measurements, and we can sum those. And sometimes we'll also sum the displacements from distributed measurements. This is it's a new concept compared to previous models. And most of the model developers realize that this is actually a more convenient way to handle particularly parallel principal ruptures. The site or the complexities that go into surface ruptures are related to event-specific things and site-specific things. And it turns out that that is really difficult to capture in a forward model. And a few different groups tried to develop parameters for site complexity, and we're not quite there yet. So by using an aggregated displacement, we're capturing all of the displacements, we think, and not missing any that is parsed onto different ruptures that we don't have the ability to model at this time. And it's probably worth mentioning that the aggregated displacement, it's not actually in the database. The model teams developed their own methods for creating the aggregated values. So that's part of the model variability, but it turns out it's actually pretty small. The variability between the models is pretty small. Excuse me. So we have talked about principal fault displacement, and aggregated's treated the same way. We're still doing that probability density function to describe the displacement amplitude. We still think about location scaling and magnitude scaling. And for distributed fault displacement models, that's really is the same thing. The concepts are similar to principal fault displacement models. We're still describing displacement as a probability density function. For the most part, most models for distributed fault displacements are not really capturing any launch strike variability in most models, but instead the distance parameter is, or the location parameter is distance from principal rupture. Still high level, same concepts. And for distributed fault displacement, most of the models are conditioned on average displacement or maximum displacement in the principal rupture event. So with that, maybe a little bit of concept of how the models are developed and the different components of the models. We have for the FDHI project now 4 new models for principal or aggregated fault displacement. Rob Moss updated his 2011 work. It's still just for reverse faulting. Nico Kuhn at UCLA developed a new model with colleagues at UCLA and PG&E. And that model is, there's different formulations, but they apply different formulations for each style of faulting, but the model, you can use it for each style. Brian Cho updated the Peterson 2011 model, and it's still just for strike slip faulting. And then Greg Lavrentiadis and Norm Abramson also developed a new model, also for all styles of faulting. So this table here on the right is kind of a high-level summary of the model formulations in the new models and what is predicted. So the formulation gives us an idea of what is predicted, which we can define over here, and then how the aleatory variability is modeled. This is important maybe for folks that are coming from ground motions and are used to seeing all models just treated as log normal. In fault displacements, we have to deal with all kinds of different statistical distributions. And so it's nice to highlight that here like this. So maybe just for example, just look at the new Moss model. They have two different alternative formulations for maximum and average displacements. And in this case, they are predicting principal displacement, principal vertical slip. The other three models all predict aggregated, they all predict the net slip component, and the KEA and LA use the same definition of aggregated in that they are thumbing principal and distributed displacements across a zone, whereas Cho et al. Are just summing the principal displacements. And we'll say that the Cho et al. Model, they offer multiple formulations, but the preferred one is this negative exponentially modified Gaussian distribution. So that's what's recommended for use cases. So that was for principal or aggregated fault displacement. There are also two new models for distributed fault displacement amplitude, one by Rob Moss, and then another by Greg Lavrentiadis. Rob's model, again, still just for reverse faulting, but he has different predictions for hanging wall and footwall side. And the other teams are planning to start working on distributed displacements next year. So it'll be separate publications from these two folks. And then there are also a couple new models for various conditional probabilities of surface rupture. Again, for Rob Moss, he has models for the distributed surface rupture probability, reverse faulting, several different models for hanging wall and footwall side distributed ruptures. And then Greg's model, this is a really interesting model. It's very different than any other model, and it's worthy of its own 60-minute talk. But essentially, they have their aggregated displacement model is like a backbone model built off of the fault segmentation, and so they capture rupture gaps in the rupture, as well as places where we don't have principal surface rupture. But these components are all kind of tangled together, so to speak, in their full model. So when they have a rupture gap probability model and a principal surface rupture probability model, it's specific to their overall modeling approach, and you can't use it with other models. But it's very cool because it's a very solid standalone cohesive model. And so to summarize where we are currently, there are 6 published reports, including the database report, and 3 of the 4 model reports are published. Earlier this year, we also published a report that compares the results from the new models for principal and aggregated displacement. And then I didn't get a chance to talk about this, but Greg Lavrentiadis also developed a new model for surface rupture length. And this is actually a really important element of fault displacement hazard analysis, because we're modeling the displacement as a function of location along the rupture length. And so we want to pay attention to how we're predicting or measuring the actual surface rupture length. Again, if you search for UCLA FDHI under the models or database tab, you should be able to find all of these reports. That being said, I do have to put a small word of caution on that, which is that most of the models, these three models, are changing a little bit relative to the UCLA reports that are online. The changes are minor in terms of the overall modeling approach and formulations, and even kind of broad conclusions. But some of the coefficients and other such details are changing. And then that'll change a little bit how the comparisons are done. Once the final versions are accepted in earthquake spectra, we'll make announcements and update the UCLA reports. And so that'll be in the spring, but we'll keep your eyes and ears open for the final announcements. So that is essentially where we are in the FDHI project. It's a big, fast whirlwind overview. But I wanted to maybe really, well, we mentioned at the beginning of the talk that there's a lot of active research in fault rupture and displacement hazard. So I kind of wanted to end this talk by highlighting some advancements that have happened outside of the FDHI project. And I'm sure this is an incomplete list, but I would be remiss not to draw some attention to these. So we have these weird intraplate reverse earthquakes in Australia, and Yang, Quigley, and Tamara King took a try at developing some models for probability of surface rupture and displacement amplitude along strike from those earthquakes in Australia. Our friends here in the group, Francesca and Franz, a couple years ago now, published new models for the probability of distributed rupture in normal earthquakes. And of course, the SURE database had a big update last year with adding many more events and the really elaborate rupture ranking system. And a couple months ago, maybe even just last month, I think Alba and Mike's paper on distributed rupture for strike slip events came out. So they looked at, I think it was mostly California events, but I'm trying to tackle this problem of the probability of distributed ruptures. And then earlier this year, the Pizza et al. Paper looked at the probability of surface rupture occurring anywhere for each style of faulting. And this essentially updates the Wells and Coppersmith 1993 models for the global empirical data set. And then we have it. I know Vicini and then his team is working on new models for distributed displacement and rupture probability. I think for both normal and reverse events. That's I think close to being done actually. And then finally, Chris Milliner has been looking at, he does all the optical image correlation, and so he's working with Brian Cho to develop a wide aperture model for fault displacement. So instead of a principal or aggregated fault displacement amplitude model, it would be for those total wide aperture measurements. And then finally, maybe in prep here is a little too bold to say, but I know Alessandro has been collecting lists of all the models that are available for probabilistic fault displacement analysis, all the models and their applicability and everything that we've seen over the last 25 years. And he's going to, I think, put that together into a reference volume for all of us. Excuse me. Okay, and my last slide here. So when Paolo and Francesca and Stefan were asking me about this talk, they thought it might be a good way to lead into hot topics in the FDHA fault displacement hazard analysis research. And so I wanted to end this talk with maybe some points on what probably still needs some more attention, especially for probabilistic analysis. And I promised myself I would limit this to just one slide, so it's definitely an incomplete list, but maybe it's some fun things to talk about. So distributed faulting, this drives a lot of the hazard decisions in the probabilistic framework. And there have been some recent advancements we highlighted on the last slide, but the probability of distributed rupture is so variable, and it is probably one of the most important factors in a probabilistic analysis. It really drives the hazard. And there's still a lot more work to do on this, even though there's been some really good progress in the last 2 years. Another fun thing, I think, is that the probabilistic framework gives us a nice, fun, clean numerical way to capture variability and uncertainty in rupture location. The only model that I think I know of for this is the Peterson model from 2011, which they updated in 2019. And this is interesting because it's a mix of mapping accuracy and repeatability in different earthquakes. But there's only one model available, and we can do better than that, I think. And I know Chelsea Scott and her colleagues at ASU have started looking into this, for example. And then maybe the last one that I'll point out here is surface ruptures can be really complex. And there's a lot of event and site-specific variables that drive this. In a lot of cases, we probably don't understand them all that well. And because this is just such a big, messy problem, most of the new models in the FDHI project use that aggregated displacement metric so that they could sidestep trying to make a parameter that you can use in forward prediction for rupture complexity. But we ultimately need to figure out how to solve this problem one way or another. So I know Austin Elliott and some of his research group at USGS are looking into this. And that this is just there's so many more things to do, but these were the kind of the interests of mine I thought I would bring up. So I think that's it. That's all I had. And I'll be honest, I can't see anyone. I can't see the chat. I think I'm just talking to a wall. So I'm going to stop sharing so that faces come back. Yeah, there we go.
Thanks, Alex. Thank
Thanks.
you.
I'm so sorry if anyone was trying to flag me down during this.
Yeah, we lost audio like 30 minutes ago, Alex. So
great. Hope everyone went and got a coffee.
Thank you, Alex. Thank you, Alex.
Thank you so much.
Thanks. Really. Thank you very much for your very clear, complete overview of the project with many insights, and also for thank you for highlighting some hot topics.
Great. Yeah.
I think we can ask people to raise hand and ask questions.
I see Bruno is typing. I see the little dots that say Bruno Pace is typing.
No questions?
Oh, Stefan has his
Stefan
hand raised.
has,
Yeah.
I have a question. I have several questions, but one, I'm sorry, I acknowledge that I was not very present during the last meetings. Can you give some words about the Greg model for predicting the surface structure length?
Oh, yes. Just so it is they consider width and width bounded conditions, right? So there's this question of, in a big earthquake, does that seismogenic base, does it kind of bleed down a little bit, or is it a hard floor? And then different models that have width bounded and width unbounded. It's the results are not significantly different than some of the other surface rupture length models, but it is a more, how do you say, like a seismologically consistent treatment. They use some seismic source, kind of point source, or not point source. What do you call the the circular and the growth of rupture. So it's a seismologically consistent model based on a larger data set. It's still, the formulation is still very simple. Like you're used to just, plugging in, I don't know, width and area and things like that, and magnitude. It still has all your simple predictor variables that you would expect.
Okay, thank you.
Other questions? Yes, please, Fia.
Hey, hi everyone. Ciao, Alex.
Hey, this is you.
Thank you for your presentation. I was just curious about the aggregated displacement. How is that to be used in eventually in BFDHA? Like if the displacement parameters are from various primary faults, is there like an idea how it should be applied in
Yeah,
modeling?
that's a great question. So some of the models have given kind of like, for example, the Kuhn model gives a breakdown of the relative contribution of the aggregated values from, say, the number of ruptures. But we haven't gone so far as to make a recommendation. The overall concept is that this aggregated displacement is a budget, and you still need to do some site-specific evaluation to decide, there's, at my site location, there's only one fault, so all of this displacement should occur on this fault. Or you say, we've got parallel ruptures and a distributed rupture, and then unfortunately it is still up to a site-specific analyst decision on how to partition that aggregated value. Does that kind of make sense?
Yeah, sure.
Yeah.
Thank you.
It's a kind of maximum threshold you can, no? The budget.
Yeah. We think we think it is the budget of discrete displacement. Now you have other things like the continuous inelastic deformation that can be captured with like, how do you say, like baseline surveys or optical image correlation, and that's inelastic. But the idea with aggregated is that it's that discrete on fault budget.
Any other question? I have one. I am also curious from the Greg model, but about probability of surface rupture. It is a kind of model to calculate the probability of having no rupture, a gap, if I understood well. But is it empirical? Is that from empirical data or not?
Yeah. So this model is so cool, and it's worthy of its own 60-minute talk. And I'll do my best here to maybe do a summary, but essentially they have the full rupture, and we know that ruptures are segmented. probably, right? And actually, maybe I can share my screen, but do you remember I showed a slip profile from Superstition Hills? Yeah, you see those really clear, how do you call them, little rainbows of slip for the different segments. So their backbone model actually is based on those segments. And then they have an aleatory variability model that's, if you know how many segments you have in your rupture, you can do that. Otherwise, it's treated as aleatory variability. And when we have segments, that means we have a gap somewhere, right? Even if it's maybe not a launch strike, maybe it's a step over, but it's still a gap in rupture. And so when they do the aleatory variability or user input for the segments, they are also capturing that gap probability or where a spot where there's no principal surface rupture. And the kind of the important thing there that I think it will be obvious in their paper, but some of the other rupture probability models, they're standalone models, and you can mix it with any fault displacement model because it just scales that y-axis in the hazard curve. But because the Greg and Norm's model is it's all tied to that backbone aggregated displacement model for the segmented ruptures, their rupture probability models can't be, or shouldn't be, I should say, applied to other models. So,
Okay.
I don't know if maybe that's not the best answer. I don't think Greg
is that published in the reports or not yet?
Very soon. It's accepted to Earthquake Spectra. So
yeah, okay.
And yeah, we'll make an announcement.
Yeah. Thanks.
So,
Thanks a lot.
Yeah. It's a very clever new approach that I don't think we've seen yet in fault displacement analysis. And I didn't get a chance to say, but like all of these new models kind of have something different. The Kuhn model uses Bayesian methods, and so the epistemic uncertainty in the model is actually quantified, and that's not particularly common when you use like a frequentist approach. So
Interesting. Any other question? Again, Stefan.
The next step of development of the FDHI works, do you plan to include the geology of the superficial layers as a parameter of controlling the arrangement of the rupture or something like this? Or because you have in the database you have classified the points and the segments with the geology.
Mm-hmm. Yeah, absolutely. So that was a really surprising finding in this first set of model developments, was there were no obvious geologic controls. 3 of the 4 model groups looked at this before they did aggregated displacements, actually when they were just looking at principal. And there was not an obvious geologic control that we could, make a little equation, with a couple of variables that would improve the models.
Prediction, okay.
So that's kind of the motivation of, I mean, there's got to be something there, right? I mean, it's so unintuitive that we can't find a geologic proxy for rupture complexity or displacement amplitude. But it's just going to take a little more time, and that's why we're working with some folks at the USGS, Austin Elliott and Steve DeLon, and some of their postdocs and whatnot. They're, I think, trying to tackle it from rupture complexity problem, because rupture complexity relates to displacement amplitude. They're 2 sides of the same coin. So one of those problems will solve it, hopefully.
Yeah. Please, can you remember us which database you used for classifying the ruptures based on geology? It was the different types of geological maps, or you?
Yeah, so we used generally small scale maps and record the lithology, right? So maybe, I don't know, like 60,000 kind of 1 to 60,000 scale maps. So maybe that's some of the challenges, that those maps are a little too, how do you say, the scale is not great. But we have lithologic descriptions, and then we made 4 different geologic categories. A young alluvium, so Holocene alluvium, older alluvium, undifferentiated, so sometimes we don't know the age, we just know it's alluvium, and bedrock.
Yeah. But this is great. This is the first database having also sure as only few events have this kind of information. So it's a great work.
I think only one.
Yeah.
Maybe only
About a little over half of the earthquakes in the database have geologic information, particularly earthquakes in Asia, mostly Asia. Yeah, most of it, we don't have good geologic maps for a lot of Southeast Asia and even the Turkey corridor. So georeferenced maps, I should say. So some events don't have geologic data.
Okay. I don't know if we don't have more questions. I think, no, Francesca, we have some news for the next talk.
Oh, yes, we are planning to have the next talk by the end of November. And Chelsea Scott and Rachel Adams should be the speakers. We are trying to define in a few days the title and the date. So soon I will send you all a message for the next talk. And if anyone wants to, show up and ask and or suggest topics or speakers, we are all ears. So you can suggest interesting topics.
So I think it's thanks again, Alex, for your talk.
Oh, yeah, thank you so much for this opportunity. I really appreciate it.
So see you to the next talk series.
Perfect.
Okay.
Thanks. Bye-bye, everyone.
Bye-bye.